Fluorine is a chemical element with symbol F and atomic number 9. It is the lightest halogen and exists as a highly toxic pale yellow diatomic gas at standard conditions. As the most electronegative element, it is extremely reactive. Almost all other elements, including some noble gases, form compounds with fluorine. Among the elements, fluorine ranks 24th in universal abundance and 13th in terrestrial abundance. Fluorite, the primary mineral source of fluorine, was first described in 1529, as it was added to metal ores to lower their melting points for smelting. The Latin verb fluor, meaning flow, became associated with it. Proposed as an element in 1810, fluorine proved difficult and dangerous to separate from its compounds, and several early experimenters died or sustained injuries from their attempts. Only in 1886 did French chemist Henri Moissan isolate elemental fluorine using low-temperature electrolysis, a process still employed for modern production. Industrial synthesis of fluorine gas for uranium enrichment, its largest application, began during the Manhattan Project in World War II. Owing to the expense of refining pure fluorine, most commercial applications of the element involve the use of its compounds, with about half of mined fluorite used in steel making. The rest is converted into corrosive hydrogen fluoride en route to various organic fluorides, or into cryolite, which plays a key role in aluminium refining. Organic fluorides have very high chemical and thermal stability. Their major uses are as refrigerants, electrical insulation and cookware, the last as PTFE. Pharmaceuticals such as atorvastatin and fluoxetine also contain fluorine, and the fluoride ion inhibits dental cavities, and so finds use in toothpaste and water fluoridation. Global fluorochemical sales amount to over $15 billion a year. Fluorocarbon gases are generally greenhouse gases with global warming potentials 100 to 20,000 times that of carbon dioxide. Organofluorine compounds persist in the environment due to the strength of the carbon-fluorine bond. Fluorine has no known metabolic role in mammals. A few plants synthesize organofluorine poisons which deter herbivores. Characteristics: electron configuration: fluorine atoms have 9 electrons, 1 fewer than neon, and electron configuration 1s22s 22p5, 2 electrons in a filled inner shell and 7 in an outer shell, requiring 1 more to be filled. The outer electrons are ineffective at nuclear shielding, and experience a high effective nuclear charge of 9-2 = 7. This affects the atom's physical properties. Fluorine's first ionization energy is third highest among all elements, behind helium and neon, which complicates the removal of electrons from neutral fluorine atoms. It also has a high electron affinity, second only to chlorine, and tends to capture an electron to become isoelectronic with the noble gas neon. It has the highest electronegativity of any element. Fluorine atoms have a small covalent radius of around 60 picometers, similar to those of its period neighbors oxygen and neon. Reactivity: the bond energy of difluorine is much lower than that of either Cl2 or Br2 and similar to the easily cleaved peroxide bond. This, along with high electronegativity, accounts for fluorine's easy dissociation, high reactivity and strong bonds to non-fluorine atoms. Conversely, bonds to other atoms are very strong because of fluorine's high electronegativity. Unreactive substances like powdered steel, glass fragments, and asbestos fibers react quickly with cold fluorine gas. Wood and water spontaneously combust under a fluorine jet. Reactions of elemental fluorine with metals require varying conditions. Alkali metals cause explosions and alkaline earth metals display vigorous activity in bulk to prevent passivation from the formation of metal fluoride layers. Most other metals such as aluminium and iron must be powdered, and noble metals require pure fluorine gas at 300 to 450 degrees Celsius. Some solid nonmetal react vigorously in liquid air temperature. Fluorine, hydrogen sulfide and sulfur dioxide combine readily with fluorine, the latter sometimes explosively. Sulfuric acid exhibits much less activity, requiring elevated temperatures. Hydrogen, like some of the alkali metals, reacts explosively with fluorine. Carbon, as lampblack, reacts at room temperature to yield fluoromethane. Graphite combines with fluorine above 400 degrees Celsius to produce non-stoichiometric carbon monofluoride. Higher temperatures generate gaseous fluorocarbons, sometimes with explosions. Carbon dioxide and carbon monoxide react at or just above room temperature, whereas paraffins and other organic chemicals generate strong reactions. Even fully substituted haloalkanes such as carbon tetrachloride, normally incombustible, may explode. Although nitrogen trifluoride is stable, nitrogen requires an electric discharge at elevated temperatures for reaction due to its very strong triple bond. Ammonia may react explosively. Oxygen does not combine with fluorine under ambient conditions, but can be made to using electric discharge at low temperatures and pressures. The products tend to disintegrate into their constituent elements when heated. Heavier halogens react readily with fluorine, as does the noble gas radon. Of the other noble gases, only xenon and krypton react under special conditions. Phases at room temperature. Fluorine is a gas of diatomic molecules, pale yellow when pure. It has a characteristic pungent odor detectable at 20 ppb. Fluorine condenses into a bright yellow liquid at -188 degrees Celsius, a transition temperature similar to those of oxygen and nitrogen. Fluorine has two solid forms, alpha and beta fluorine. The latter crystallizes at -220 degrees Celsius and is transparent and soft, with the same disordered cubic structure of freshly crystallized solid oxygen, unlike the orthorhombic systems of other solid halogens. Further cooling to -228 degrees Celsius induces a phase transition into opaque and hard alpha fluorine, which has a monoclinic structure with dense, angled layers of molecules. The transition from beta to alpha fluorine is more exothermic than the condensation of fluorine, and can be violent. Isotopes. Only one isotope of fluorine occurs naturally to any significant extent, the stable 19F that has 10 neutrons. It has a high magnetogyric ratio and exceptional sensitivity to magnetic fields, because it is also the only stable isotope. It is used in magnetic resonance imaging. 17 radioisotopes with mass numbers from 14 to 31 have been synthesized, of which 18F is the most stable with a half-life of 109.77 minutes. Other radioisotopes have half-lives less than 70 seconds. Most decay in less than half a second. The isotopes 17F and 18F undergo beta plus decay. Lighter isotopes decay via electron capture, and those heavier than 19F undergo beta minus decay or neutron emission. One metastable isomer of fluorine is known, 18 millifarads, with a half-life of 234 nanoseconds. Occurrence. Universe. Among the lighter elements, fluorine's abundance value of 400 ppb, 24th among elements in the universe, is exceptional. Other elements from carbon to magnesium are 20 or more times as common. This is because stellar nucleosynthesis processes bypass fluorine, and any fluorine atoms otherwise created have high nuclear cross-sections, allowing further fusion with hydrogen or helium to generate oxygen or neon respectively. Beyond this transient existence, 3 explanations have been proposed for the presence of fluorine. During Type II supernovae, bombardment of neon atoms by neutrinos could transmute them to fluorine. The solar wind of Wolf-Rayet stars could blow fluorine away from any hydrogen or helium atoms, or fluorine is borne out on convection currents arising from fusion in asymptotic giant branch stars. Earth. Fluorine is the 13th most common element in Earth's crust at 600 to 700 ppm by mass. Elemental fluorine in Earth's atmosphere would easily react with atmospheric water vapor, precluding its natural occurrence. It is found only in combined mineral forms, of which fluorite, fluorapatite and cryolite are the most industrially significant. Fluorite or fluorspar, colorful and abundant worldwide, is fluorine's main source. China and Mexico are the major suppliers. The U.S. led extraction in the early 20th century, but ceased mining in 1995. Although fluorapatite 3F contains most of the world's fluorine, its low mass fraction of 3.5% means that most of it is used as a phosphate. In the U.S., small quantities of fluorine compounds are obtained via fluorosilicic acid, a phosphate industry byproduct. Cryolite, once used directly in aluminium production, is the rarest and most concentrated of these three minerals. The main commercial mine on Greenland's west coast closed in 1987, and most cryolite is now synthesized. Other minerals such as topaz contain fluorine. Fluorides, unlike other halides, are insoluble and do not occur in commercially favorable concentrations in saline waters. Trace quantities of organofluorines of uncertain origin have been detected in volcanic eruptions and geothermal springs. The existence of gaseous fluorine in crystals, suggested by the smell of crushed antozonite, is contentious. A 2012 study reported the presence of 0.04% F2 by weight in antozonite, attributing these inclusions to radiation from the presence of tiny amounts of uranium. History. Early discoveries. In 1529, Georgius Agricola described fluorite as an additive used to lower the melting point of metals during smelting. He penned the Latin word fluorace for fluorite rocks. The name later evolved into fluorspar and then fluorite. The composition of fluorite was later determined to be calcium difluoride. Hydrofluoric acid was used in glass etching from 1720 onwards. Andreas Sigismund Marggraf first characterized it in 1764 when he heated fluorite with sulfuric acid, and the resulting solution corroded its glass container. Swedish chemist Carl Wilhelm Scheele repeated the experiment in 1771, and named the acidic product fluorspatscyrin. In 1810, the French physicist André-Marie Ampère suggested that hydrogen and an element analogous to chlorine constituted hydrofluoric acid. Sir Humphrey Davy proposed that this then unknown substance be named fluorine from fluoric acid and the -ine suffix of other halogens. This word, with modifications, is used in most European languages. Greek, Russian, and some others use the name FTOR or derivatives from the Greek phi theta omicron rho iota omicron sigma. The new Latin name fluorum gave the element its current symbol F. Fl was used in early papers. Isolation. Initial studies on fluorine were so dangerous that several 19th-century experimenters were deemed fluorine martyrs after misfortunes with hydrofluoric acid. Isolation of elemental fluorine was hindered by the extreme corrosiveness of both elemental fluorine itself and hydrogen fluoride, as well as the lack of a simple and suitable electrolyte. Edmund Reactivity postulated that electrolysis of pure hydrofluoric acid to generate fluorine was feasible and devised a method to produce anhydrous samples from acidified potassium bifluoride. Instead, he discovered that the resulting hydrogen fluoride did not conduct electricity. Reactivity's former student Henry Moissan persevered, and after much trial and error found that a mixture of potassium bifluoride and dry hydrogen fluoride was a conductor, enabling electrolysis to prevent rapid corrosion of the platinum in his electrochemical cells. He cooled the reaction to extremely low temperatures in a special bath and forged cells from a more resistant mixture of platinum and iridium, and used fluorite stoppers. In 1886, after 74 years of effort by many chemists, Moissan isolated elemental fluorine. In 1906, 2 months before his death, Moissan received the Nobel Prize in Chemistry, with the following citation: in recognition of the great services rendered by him in his investigation and isolation of the element fluorine. The whole world has admired the great experimental skill with which you have studied that savage beast among the elements. 1887 drawing of Moissan's apparatus. Nobel Prize photo of Moissan. Later uses the Frigidaire division of General Motors experimented with chlorofluorocarbon refrigerants in the late 1920s, and Kinetic Chemicals was formed as a joint venture between GM and DuPont in 1930, hoping to market Freon 12 as one such refrigerant. It replaced earlier and more toxic compounds, increased demand for kitchen refrigerators, and became profitable. By 1949, DuPont had bought out Kinetic and marketed several other Freon compounds. Polytetrafluoroethylene was serendipitously discovered in 1938 by Roy J. Plunkett while working on refrigerants at Kinetic, and its superlative chemical and thermal resistance lent it to accelerated commercialization and mass production. By 1941, elemental fluorine's large-scale synthesis began during World War II. Germany used high-temperature electrolysis to make tons of the planned incendiary chlorine trifluoride, and the Manhattan Project used huge quantities to produce uranium hexafluoride for uranium enrichment. Since UF6 is as corrosive as fluorine, gaseous diffusion plants required special materials: nickel for membranes, fluoropolymers for seals, and liquid fluorocarbons as coolants and lubricants. This burgeoning nuclear industry later drove post-war fluorochemical development.